All right, so here we go. Let's see. First, any questions about anything? For example, when I'm going to collect the homework exactly. So there's been numerous requests that I just officially say that this time I'm going to collect the homework at 6 a.m. on Monday morning. Anyone opposed to that? Anyone for that? All right. Okay, this time, no guarantees about any future time, but I'll run the collection script at 6 a.m. on Monday morning, or slightly later, but not earlier than that this time. Okay? Just because you're working on your projects and so on. And to make it official, I will right now send an email to the list. So here you are, homework collection will happen 6 a.m. on Monday. Okay, so there, officially that's what will happen. Okay, so other questions? Okay, so let's get going. So what I'm going to talk about today is kind of the fundamental issue of speed when you're using Python for scientific computing, numerical computing, and math type applications, where you're not just calling into some big function in some library or doing things that are I/O bound or whatever. And I like to, well, motivated by how Alan Steele, the lead developer of Magma, would describe things. I like to think about a sort of C level and a Python level, an interpreter, or more a compiled level and an interpreted level. So when you're programming with Python, it's kind of like you're down here floating around. It's easy to sort of float around and move. And, you're not going to like make some slight move and then fall 50 feet and die, or segfault your program or whatever. So that's kind of how I think about when you're working at the Python level. But then there's also a C level, or more generally a compiled level, where you have a lot more flexibility. You can do things very quickly, like this person's flying through the air very quickly, spinning around, whatever. You can also break your leg really quickly, which is kind of like, you do something with a pointer or whatever, manipulate memory in some way, and your program just segfaults. So you have a lot more power, and a lot more potential speed, but it's sort of less friendly. And probably so I don't know if I've never scuba dived and I've never kite surfed, unfortunately. And I probably like both of them. But I'm pretty sure that on the first day of scuba diving, you could do that. But on the first day of kite surfing, probably wouldn't do that. And so it's kind of similar with Python. Like in the first day, you can already write, maybe a little useful program without causing anything to completely crash and the whole program to die and bad things to happen. Although I guess with a few characters in Python, you can delete all the files in your hard drive, but as you learn. But with greater skill, you can do things that are a lot faster. So Cython is a special motor and extension to Python that, in a sense, makes it so that you can do this, but from Python, or at least writing code that looks a lot like Python. And you can do it in a nice, smooth way. You can sort of smoothly move from the nice, friendly underwater environment to flying through the air. And it's friendly. Speaking of flying, there's a fun XKCD which says, "You're flying, how?" And the person's response is, "Python." And then it says, I learned Python last night. Everything is so simple. Hello world is just print hello world. I don't know, dynamic typing, white space. Come join us, programming is fun again. It's a whole new world up here. But how are you flying? I just typed import anti-gravity. That's it. I also sampled everything in the medicine cabinet for comparison, but I think it's the Python. But in Python, you can often do ridiculously powerful stuff by just importing some module that behind the scenes does an enormous amount in some other language like C++ or something. An example being quantlib, which I added recently to the SageMath Cloud. Type import quantlib, and then you can just start flying through, doing all kinds of crazy stuff with quantitative finance. Behind the scenes, it's really running big C++ library. Okay, here's some motivation. I don't know if any of you have seen this before, but and of course you can argue endlessly about it, but I'll just show it to you because it does tell you something. This is called the Computer Language Benchmarks game. And it's, I think, hosted at, well, doesn't matter where it's hosted. So it's, basically, there are a whole bunch of different problems, such as compute the Mandelbrot set, enumerate binary trees with certain properties, et cetera, et cetera. Do something with, I don't know, it just has a bunch of described problems and also algorithms for addressing those problems. So then what people have done is in like 50 different programming languages over many, many years. This thing's been around for, I don't know, like 10 years or something. They've tried to write fast programs for solving those problems. And then they automatically benchmark all of them on a couple of different types of computers and then draw plots that show how they compare. So it gives you some rough indication of the relative speed, if you care and are willing to put in some time, of these different languages. Although when you look closely at the programs, you can see that they'll use not necessarily at all standard libraries in each language. So that is relevant. In any case, let's just look at a few of these. Here I'm comparing for the benchmarks that they have here. The two languages are C and Python. And the factor in time is how much faster, well, how much longer the Python program takes than the corresponding C program. So for example, they have something they call digits of pi. The Python program and the C program are almost the same speed. They have another one called binary trees. The Python program is 51 times as long. It takes 50 times as long for the Python program as for the C program to run. I looked closely at the source code, by the way, of the PyDigits one, and I can show it to you in a minute. It's really just a couple of operations, but with very big arbitrary precision numbers, and both of the programs are just using arbitrary precision libraries that are in C behind the scenes anyways, like they're using GMP. So it's somehow not surprising their time is similar. But on the other hand, the binary trees one, that's just like a bunch of Python code. In the Python version, and a bunch of C code in the C version, and it's not really doing much calling out to other libraries. So it's really a more fair comparison, and you see this factor of 50 difference in speed. And that's comparing those two languages. It's interesting if you click, actually if you, well, I have a link, which I'll show you. Just comparing all the languages for a given, let's see, where's that link? Well, okay, let me just find it. I mean, let's see. Oh, right, I know. So let's take one thing, which is binary trees. Here's the link, binary trees. Okay, so this is interesting because instead of just showing C and Python, it shows a large number of different languages. In fact, too large to show on one screen. So I'll put them side by side. JavaScript. Okay, so for a very, very kind of straightforward enumeration problem that just involves some for loops and so on, and actually, let me show you the code for a second so you can see what's going on. So let's look at this, and then I'll show you the timings. So binary trees in Python. Where is it? Binary trees, Python. Here's the code. They have single process and multi-processing versions. So they have, in other words, serial and parallel ones. But I mean, it's just really straightforward. This is just something that ends up dividing it up into chunks and doing it in parallel. None of the benchmark numbers I'm showing you are the parallel versions, so it's kind of irrelevant. So really, this is pretty much the entire program right there. Okay. It's just a little bit of Python code, calling some Python functions, and returning stuff. I mean, there's really, really simple Python code. Okay. And then there's a corresponding C version, if and so on. Okay, so now let's look back at what I was showing you. So this gives you a sense, if you're just doing a bunch of just core Python programming, what kind of speed comparison you might have to what you might get in C or Java, which many of you are familiar with. So the fastest of all of the languages for this particular benchmark over many years is C in this case. And in fact, if you look at all the different challenges, C pretty much wins everything. Fortran maybe should, but in any case, C actually wins everything. So, or almost everything. And so Java's close by a factor of 2, and that's pretty typical. And then if you go down, surprisingly, JavaScript is quite good. So it's like 5 times the speed of using C. But then you get way down there to Python, which isn't even shown so far. Even past Ruby, amazingly. And there it is. And that's kind of worrisome. They're using Python 3, by the way, systematically for everything, but it doesn't make much of a difference. It does beat PHP. Woohoo! And Perl. But so when you see this, you might think, okay, there's absolutely no hope they're going to use Python for any serious number crunching, where you're writing the number crunching stuff from scratch. Like if you're going to do something that maybe involves multiplying 2 matrices with floating point entries, then you'll do use Sage's matrices, or you'll do import NumPy and make NumPy arrays and multiply those, and it'll be blazingly fast. But what if you have to do some slight variation on that, where the code kind of looks like the code for matrix multiplication, but you throw in something funny along the way, and it's really kind of different code? That could easily come up in some research project. And then you're going to be in big trouble, because when you try to write it, the speed is going to look a lot like this, rather than like the other thing. And if you're 50 times slower and you're doing research, you will lose potentially to your competitors, or you won't do as interesting of research. Fortunately, there is a way that is extremely broadly used in the scientific Python community for getting around this problem. And that way is Cython. That's the way that's actually worked in practice. There's been a huge amount of work and approaches and attempts to do things kind of inspired by what's happened with Java and so on, where you have a just-in-time compiler for Python, but none of it has really been successful as far as really making something that is fast and competitive with C. With Cython, you can take specific things that you need to do, and if you're willing to put in a bit of extra work, but less work than completely switching your entire project to C, you can get exactly the same speed as C if you're willing to put in sufficient extra work. Okay? And now I'm going to show you a step-by-step example of doing exactly that. Okay? So I have a few things up here, but I'm going to skip them for the time being so that I can show you very carefully this one example in detail. And to avoid spoiling things, I will hide the output. Okay. All right, so here's the example. Compute the variance of a bunch of, wow, I guess I hid all of the, oh, that's annoying. It hides all of the friendly, like all that markdown output as well. Okay, never mind about hiding the output. Not a good idea. Should make it not hide the markdown output, because that's sort of like the commentary. Okay, so what can we do? So basically you have this tension because a lot of people find Python to be pretty nice and fun compared to other programming languages. They want to use it. They think it's relatively eloquent. I fall in that camp. And they know for a fact that, they look at Python programs and they can generally understand them. They write Python code and they can read it later. There's a lot of pluses to working with Python. And really the big minus is that it can be really dreadfully slow. So Cython helps to deal with that problem. Helps enormously. So here's a problem we're going to solve. Just a little tiny sample problem but it shows the sort of start to finish of going from something that's really slow but straightforward to implement to something that's only slightly more complicated but dramatically faster. And here we are. So the problem is compute the variance. So that's the number whose square root you take when you compute the standard deviation, a extremely basic thing in statistics. Okay, so it's the average of the squares of the differences of your numbers from the average, or from the mean. All right, so that's the thing we're computing. And I'm going to define a sequence of functions called var0, var1, var2, var3, and so on, each of which will be a little bit better than the one before it. So here's the first version, and I'll talk you through it and also evaluate it. So this one is 2 lines of code to implement the function. I can probably make it a little bigger. And the first line, it computes the sum of the numbers in V and divides that by the length. We're going to assume that the numbers in V are floating point numbers. So there's double precision floats, a very common thing to come up. If you're going to compute a variance or standard deviation, probably the numbers you're going to compute it of are floating point numbers. It's just very likely. So here's an example of what such a list might look like. So you compute the sum of them and divide by the length. That's what I'll call M. And then the next line, line 124, we're going to take the sum of the differences of each element of V from the mean that we just computed, square it, and then take that result and divide by the length. Okay? You could probably have written this easily during the first week of class. That could have been one of the exercises at the beginning. So any questions about it? Note, by the way, I'm using double star instead of a caret for exponentiation because I want to keep it as pure Python. In fact, let me put %Python right here. That will ensure that there's no Sage pre-parsing causing any surprises. Okay, and I'll make a new random list. And let's run it, see what we get. So we get some number. And now I'm curious how long it takes. So first, 10 is kind of a really, really small number of numbers to take the variance of. So let's make a larger list so that at least our benchmark will be slightly interesting. So now we have 10,000 numbers. They're random. They're all between 0 and 1. And let's compute the variance. So there it goes. And it did 100, so the time it command, %time it, runs the code that's after it many, many times, depending on how long it takes. It'll do it like 6 times if it doesn't take very long, but it'll do it a lot more times if it takes very little time. So the average time it took per loop during the best one was 4 milliseconds. So there we are. So it takes 4 milliseconds using this Python implementation, which might at first seem like, oh, that's perfectly fine, only 4 milliseconds. But what if you need to compute 10,000 of these variances? Because you're working at a hedge fund and you have to compute some huge number of standard deviations or something because it's relevant for a whole bunch of different financial time series. So 10,000 of those might take a while. So a millisecond is 1,000th of a second. So 10,000 of those, that's going to take 40 seconds. And that's kind of a long time. And what if it's, what if you need to do 1 million of these? Then you're in big trouble. So it needs to be a lot faster than that. Okay, but that's what we got at the beginning. Now what I'm going to do is rewrite this in Cython. It's going to be exactly the same. I'm not going to change a single letter in the implementation. It's going to be identical code, but I'll write it in Cython. The only difference is I'm going to put %Cython at the top of the block. And on Monday, I'll show you how, if you want to make a Cython program that's completely separate, has nothing to do with Sage a priori, it's just something you could import into any existing Python code. I'll show you how to do that as well, which is well supported. But for a first pass, it's really good to just play around with the notebook. Okay, so now let's rewrite the above program in Cython. Okay, Wasn't too hard. It's identical to what I had before. Unfortunately, it's not going to give much of a speed up either, as the output that you can see already suggests. So 2.44. So that was 4.07 versus 2.44. So we got a speed up of 1.66. That is to say, the Python version takes 66% longer than the Python version. By the way, I fixed the bug so that show auto-generated code, or not. That's weird, because that is not right. What the heck? Absolutely certain I fixed this bug. It's critical that you see the correct auto-generated code. And I think I have to restart the project server to get the bug fix to take effect. So that's going to take a second. But I'll talk about this for a second first, and then we'll look at the auto-generated code. If it doesn't work, I'll just pull it up on my virtual machine or something. But this is the same code as what we had above. What happens is that line by line, this is converted into C code, compiled, and then linked in dynamically to our running Python session. And turns out that it's a little bit faster, but not much faster, because really all the C code does is so Python itself is really just a big C program. And all the compiled version of this does is simply call the same functions in Python viewed as a C program as the Python interpreter does when it's running the code up there. It's a little bit faster because there's kind of a little less overhead, but it's more or less doing exactly the same thing under the hood. So we don't get much of a speed up. Let me try this again, see if this works. Show, it doesn't look. Nope. Okay, don't know why. I mean, the new one's pretty similar. It just goes to this directory. There it is. Okay, so the bug fix was to change it so that it goes to what it currently appears to go to this other URL. So at least I can show it to you. I just sort of hacked it in. It'll be fixed properly shortly. The first line gets converted from, so what happens here is this shows each of the lines of code that I typed, plus some little header information. And when I click on a given line, it expands it to show you the corresponding C code. So that one line gets turned into all of this C code. So it's really a whole bunch of code. So there's something called the Python C API, and you can view Python itself, the Python interpreter, as simply being a big C program with a bunch of functions it makes available at the C level, such as PyObject length. Given a Python object, it'll give you the length of that Python object. PyObject is double, it converts a Python object to a double, etc., etc. PyTuple setItem, this sets an element of a tuple, but all these are calls into the Python C library. And so what Cython does is it turns that one line, line 7, into a whole bunch of code. What it does is it parses the code that you wrote and then generates this code right here. And it's really daunting. I mean, it's always very long. And then the next one, if we click here, we'll see what the second line gets turned into. And again, it's just, I mean, it's painful to read because the variable names are all big and it's all kinds of error checking in there and so on. Notice it turned that sum into a for loop in C. So it's big, but it's actually faster. Okay, let's go back here. Now, this doesn't give us much of a speed up, but look at the next one. So here, now I'm starting to do something. I'm going to declare some types. So these two lines are exactly the same as they were before, but I'm declaring B to be a list. That saves a little bit of time. So instead of the code having to figure out whether B is a list or some other iterable object, it'll just assume from the start, or it'll convert it so it's definitely a list everywhere down here. There's some very small savings from that. But also M and X, anywhere they appear here, which is, for example, right here, they will be C-level doubles. And so you might get a little bit of a speed up from declaring these types. Okay, so let's try it out. So again, it's A, it turns all the code into C code. B, it runs the GCC compiler on that code. And then it links it into our running session, which takes a little bit of time. So let's benchmark it on our new sample data. And it took 800 microseconds. So compared to the original pure Python version, that's 5 times faster. Okay, so that's somewhat good, but it's not really that exciting. Yes?
Didn't it run 5 times as many loops, though?
It still gives you the time per loop. So when we are waiting, because it's faster, without us dying of impatience, it can do more tests, and that's what it does. So the number of times it loops in timing the evaluation of this depends on how long it takes to do the first evaluation of this. So yeah, there's a standard module in Python called timeit, and if you just type timeit Python into Google, you'll be able to read the documentation. But they talk about how timeit avoids many of the pitfalls of benchmarking to give you a reasonable estimate of how you're doing. So what they did was, if this took like a second each, it would have only run 5 loops. But because it's so fast to run it, it runs it 625 times. But then it takes that total time and divides it by 625. And then it does that again. And then it does that again. And takes the best of those. Okay, so that's really good. However, it's not good enough. We've only sped things up by a factor of 5. So maybe I'll talk for a second. So in Cython, the way you declare the data type of a variable is you say cdef, which is a keyword that's not in Python. It's introduced in Cython. It's not in any other language. And then you give a data type. You can use any standard C data type right here. You can also use additional ones that you declare that are say C++ types or structs. There are many other types of data types you can use right there. And it gets interesting how you do that. There's a website, cython.org, and a wiki page, and so on, which has lots of tutorials. There's a lot of explanation about how to do more and more complicated things. But you can take like a complicated C++ class that's templated and use it here, for example. And the C++ support, that was something that was added as a Google Summer Code project about 2 years ago. Yes? You mean like float, that data type?
Yeah, I mean, isn't it just an underlying?
It's really kind of different. So it's actually, so let me see if I search for Pi object. See if I can get the C struct of a Pi object. Well, instead of showing you some massive struct, I'll just tell you every single Python object, except a few special cases like small Python ints, which have some tricky representation, is basically there's this big C-level struct that wraps that Python object. And so even if it's just a double sort of that you're representing, there's a lot of other information there. And so there's a huge amount of overhead with the creation of almost any Python object. So if you look at the Python C API reference manual and so on, you'll see that like a Pi object, it's a C struct, and it's just really big. So when you make a float in Python, when you do this, like float 7, that one thing right there, it's really a C struct, and there is a C double there, but there's other stuff there as well. For example, there's memory management that involves reference counting. So when I say A equals float 7, B equals A, C equals A, there are now 3 references to that object in memory. That one object has 3 references. Somewhere in that C struct, you have a counter that is set to 3 right now rather than 1. And there's this code that every time you, for example, if you were to say DELB, so that deletes B, so now B is no longer defined, that means there's one less reference to that object. And so some additional data in addition to that double that's stored in there gets decremented by 1. And at some point when it eventually gets to 0, then the whole object's freed. So it's really pretty complicated. Yes. Yeah, every single object that you create in Python is an object. I mean, and hence there's potentially a lot of overhead. But in Cython, these like M and X, they're just double. They are 64 bits of data in the computer, nothing else. You know exactly what they are. Total control. Okay? And it's faster. All right, let's make it even faster. So let me show you right here, we're calling Python's sum function. Right there. And that is probably causing us a lot of pain. So let's get rid of that. What this does is it takes our list. Python then has its own implementation of sum up the entries in the list. Maybe that is expensive. So let's just write our own sum. It's going to be ugly. Certainly be more than 3 letters long, but it'll allow us to completely avoid calling Python's sum function. Because that sum function is calling probably plus over and over again. The sum function in Python doesn't know that every single thing it's going to be summing up is a double. Because right, V is just some generic list. It could be that as the sum function is going through and adding up the elements of V, you have like a number, a number, a number, and a picture of your mom, and then another number. And you have all kinds of funny stuff as you're going along, right? Python just does one, then does the next one, does the next one. It doesn't know that it's a uniform list. In fact, I mean, it's only uniform because we made it that way at the top. So let's write our own sum function where it's going to take each entry, convert it to a double as it's doing the sum, and if one of them isn't a double, it's just going to stop immediately with an error, and if they're all doubles, it'll work. So let's just do that. So the next version, I hope, will be faster, and the way it works is we're not going to call Python sum function, but do the sum ourselves. Okay, we're going to do the sum ourselves. So here it is. So this still is like everything except the CW double is just standard Python code, which is actually really, really nice. And Cython is not like that for a long time. It used to be that if you wanted to make a for loop, they would get converted directly into a C-level for loop. You had to do a lot of compressions. This is, in any case, all I'm doing is getting rid of calling a sum function in Python. That's the point of this. But it still has to iterate through V, so there's a lot of work there. But what it's doing is it says for x in V. So what that does is it gets each of the entries out of V and turns it into a double because x has type double, and then it does that sum. So at least the plus right here is just going to be a single line of C code. There's no type. There's not going to be any error checking. There's no Python involved at all. S is a double, X is a double. It adds it in. So that's going to be a big savings. And that division is just straight C because N is a double and S is a double. So basically every point here in which arithmetic happens is just addition, multiplication, or division of C-level objects, which is like super, super fast in the computer. Whereas when you do addition with Python objects, it has to figure out what the add even means, and might have to do some complicated method resolution and stuff to figure out how to add two things. I also got rid of the **2 and just put x minus m times x minus m because I don't know, I was just worried that maybe it was literally calling some exponentiation library. I don't know. I mean, you have to look at the source code, but I figured that was a good idea to just write it this way. Okay, so let's see how this does speed-wise. So compile it. which should, again, it takes like a couple of seconds to compile. And then run it, and it took 194 seconds, microseconds instead of the 4.0, I forgot, 3 or something from before, 4.07 from our original Python version. Okay, so that's almost 20 times faster than the original one. So we're computing our variance in 194 microseconds instead of 4 milliseconds. So that's really an improvement. And the main difference that we made was to get rid of the call to Python sum. Okay, any ideas for what else we might do to make this faster? Or to make something related to this faster? Yeah. Wait, what did you say exactly? Yeah, the parameter v, that list is a Python list. So there's no guarantee that each of the entries are floats. It's a lot of work to convert them all, which I'm doing twice. Here and there, I'm converting them all to floats from whatever they happen to be, okay? So instead, let's make up a whole new data type from scratch that is a bunch of floats, okay? That's what it's going to be. It's going to be an array of floats. And let's do it. So here's how I'm going to do that. I think to fit it on the screen, I have to make it slightly smaller. Yep. Okay, here it is. So in Cython, you can define classes that have, so if you just do class something without cdef in front of it, it just makes a normal Python class. And instances of that class can only have Python attributes. However, if you make a cdef class, you just put the cdef keyword before the class, then any instance of the class can have C-level attributes. So we can make it have a pointer to a double, that is an array of doubles in C, and an integer, an actual C integer as basically every instance of this class. It'll still be a Python object, but so there's reference counting and so on, but instead of it having only other Python objects that are its attributes, in addition to that, you can, well, not in addition, but instead of that, you have a double star and an int, okay? So this is, it gets more technical here, but here's the init method. And what we're going to do right here is allocate, and I have not freed any of the memory. I just didn't write that yet. What we're going to do is allocate memory using malloc. And sage malloc is a wrapper around malloc that, I'm trying to remember why we have that. I think it uses the Python. So Python gets a big heap that it allocates all of its objects in. I think sage malloc uses the Python heap rather than its own memory space, which makes Python happier because the Python interpreter has a better sense of the total amount of memory that's being used by Python, which is best practice for writing Python extensions. In any case, what we do is we allocate enough memory to hold all the entries of V, and then we store them, but not as a Python list. Instead, we store them as a C array. Exactly what's going on here with allocating memory and pointers should only make sense to you if you have some familiarity with C. Otherwise, unfortunately, it probably won't make a lot of sense exactly what's going on right there. Yes, so in the C language, exactly what's right here that's highlighted on line 212 would be parentheses. That's the casting in C. In Cython, that's too ambiguous relative to how Python works, so instead use angle brackets. But otherwise, that's exactly converted just to the normal C casting. And that's necessary. Otherwise, so malloc gives you back a void star, and V is or self.v is a double star, and so you can't do that assignment in C. Okay, so that makes it so that our data is an array of doubles instead of just a Python object. And now let's write a method to compute the variance. That's right here. And it's almost exactly the same. I copied and pasted the code from above, except instead of going for x in v, I have to be a little more verbose. I say for I in range n, and then I get self.v square brackets I. So that gives me the ith entry of that C array. Right there. And then everything else is the same as before. The only difference now is we're, again, just getting the ith entry of our C array. Okay, any questions about this? Yes?
For the init, aren't you passing the list already?
Yes.
So is that what you want to do as far as like speed up?
Well, I'm not going to benchmark the conversion right here. I'm only going to benchmark calling the variance function. So in a sense, I'm just getting rid of the overhead of doing that. If you're going to do this in an actual application, you would never create the list v directly that way. What you do is you'd write a data structure like this, and then you'd have a method maybe randomize that would randomize all the entries.
Yeah, just for this example.
Yeah. And if you want to see a very complete example of that, look at stats.timeSeries. It is just a double star, and it has a large number of methods for just directly working with that. Or alternatively, you can also look at NumPy's array type for a vastly more complicated example of a much more general thing. Okay, so now you're probably wondering whether this works and how fast it is. And I feel a little guilty. There's no, let me just point out, if you run this over and over again, your mallocing memory, that is your allocating memory, it's never going to get freed ever. It's a memory leak the way I've written this. You have to add another method, I think, called del. And there you would put sage underscore free self.v. So I think I'll do that. What that does is it frees up the memory that you allocated above. If you don't put that in, though, and you just create lots of these objects, you'll just notice that the memory usage of your program keeps going up until you run out of memory. I mean, if you're creating more and more of these objects. Okay, I'm now compiling this code. And again, it worked. And now let's make an instance of it. So this VD, I didn't make a repr method, so it just uses some default repr method. But I just want to point out that these CDEF classes, you can add all the same methods that you would normally add for Python classes. There's a few subtleties with comparisons and so on, but for the most part, they're very similar to normal Python classes. The one difference is, though you can use inheritance, you can only do single inheritance. These don't support multiple inheritance, that is, deriving from multiple distinct classes. So you can only derive from one class. But otherwise, they are very similar to normal Python classes. Okay, so we have our VD, and let's compute the variance. You can already see what the timing was last time I tried this, 29 microseconds. Okay, so now it's 4.07 or whatever it was versus 0.0298. So our new code is well over 100 times faster than very similar code written in straight Python. But it's not 100 times longer, but it is significantly longer. And it uses some like archaic things like memory allocation and deallocation in C and so on. But if we were in the middle of some big Python program and we had a list or a bunch of lists and we needed to do a bunch of things with standard deviations, you can see how, or variances, you can see how you write a little bit of code like this, the rest of the code is in Python, and the whole thing is fast as a result. Usually with programs, most of the program uses very little of the time, and there's a little part that's kind of the bottleneck. And if you figure out what that is, then in some cases, if the bottleneck is because it just involves some number crunching where Python isn't particularly good, then you can rewrite that part in Cython, and then it will be fast. And there's an enormous amount of Python code like this. Often when you, if you install a third-party Python library, if you do pip install something, you'll find there's a whole bunch of Python code, and then as it's installing, you'll see that it compiles something. And often there'll be like one or two files where it compiles something so that it can maybe call into some C library or some speed critical part of the code will be fast. Okay, that's the way to write Python code if you need it to be fast. If you're just playing around and you just want to do some experiments, you don't have to worry about that at all. But if you're going to write something serious that's supposed to be competitive with code people might write in C, that's absolutely critical. You have to do that in a lot of cases, unfortunately. Currently, I mean, maybe in 5 years it'll be completely different, and there'll be some other way of compiling Python code that's a lot better. I know that the guy who wrote NumPy, Travis Oliphant, got a large DARPA grant about 2 years ago, specifically for writing a Python compiler, which would be sort of would allow you to hopefully get speed ups like you get with Cython without having to know anything about C. So we'll see where that goes. So there is definitely a lot of support behind that sort of direction. All kinds of surprises happen. Like JavaScript was very slow for a long, long time and suddenly got a lot faster due to people at Mozilla and also people at Google writing really, really, really clever JavaScript just-in-time compilers. So these things just surprisingly change. That said, I'm a little dubious that you can make Python as fast as C without just writing code that kind of looks like C with Python notation. This looks a lot like Python, it's just that there's a couple of lines where you use a CDEF and you get to use a C data type. And the speed up we got, if you sit down and write something to do the same thing in just straight C, you're going to get about that speed. So the bottleneck, like the part that actually is taking the time, we're going to get the same speed as C by doing this. If we look at this function variance right here, like it's all just converted line for line directly to C. Okay. All right, we have a little bit of time. By the way, here's why it's called Cython. So I was trying to come up with a name for this project. It was called Pyrex. We were forking a project called Pyrex. And Pyrex isn't the greatest name. If you try to Google Pyrex, you'll discover that they make like lab equipment and glassware and stuff, you know, cooking and stuff. It's everywhere. Like they just dominate the search for Pyrex. It also kind of isn't really that suggestive of what's going on here. Cython, on the other hand, suggests C and Python. Also, at the time when I named it Cython, if you Google, that was the top hit. This punk rocker guy in England named Cython. And I didn't think it would be difficult to, I didn't think he would sue me for something, and I didn't think it would be difficult to get a higher ranking. So thank you, Cython, for inspiring the name. All right, with that, I hope you have a good weekend, and I'll see everybody on Monday.
That's not it.